Let's do some stats together. Now we need to more than ever. Let's do some stats together now. Residuals, outliers, and regression diagnostics coming up right away. Residual analysis. This involves us looking at the errors, residual error, synonyms. Lots of information in those errors, particularly as regards to problems with our model and any kind of missing variables that should be in the model that aren't. Right? They show up somewhere, they show up in error. Right? So all those things that we missed show up in error. And so we analyze that error. Makes sense, right? Because the things that we missed, the things that aren't quite right, their impact typically shows up in error. So by examining those errors, we can help to diagnose or discover any problem areas in our model. And there's going to be two big ones that we'll talk about in this particular unit. There'll be a couple others later on. One of the big ones is we assume that variance is constant. The variance of those errors are constant across all values of x. It's a very important assumption. It's one of our basic 4 assumptions. How do we know that assumption is valid? How do we know that it hasn't been violated? Well, we do that by conducting a test. We can look at graphs too, and graphs give us some good information, but sometimes graphs get a little mucky when we have a multiple linear regression and we're looking at a zillion graphs. A little unfun. However, we can do a test, 6 steps to that statistical test, and we can do a test and we can see if we have non-constant variance or not. Next big thing is we're worried about highly influential observations. And those typically fall into 2 categories. Really, really large values of y, really, really, really small values of y. And the other category is really, really, really big values of x, and really, really, really small values of x. These things are situations and potential observations where they have a bigger influence on our regression model than, let's say, others. And sometimes that's a problem and sometimes it's not, okay? But we can discover those by looking at the errors. So a lot of stuff is in those errors. A lot of diagnostics can be found in the errors, and then looking at those really, really big observations, really, really small observations, influential observations. Okay. So those errors, calculating errors, not hard, right? It's just how much what we observed and what we actually had minus what our model predicts, aka the line, right? And the difference, we want to make sure that there's no pattern in that difference. We want that difference to be random. Because if there's a pattern, now that could mean we have omitted variables. And if we have omitted variables, well, we want to get those variables in that model, right? So we don't want any pattern in those errors. We want it completely random so that it's just not caused by a missing variable. I mean, that'd be the biggest, that's usually the biggest problem, missing variable, or we think this is a linear relationship and it's not. Okay. So we look at our errors and we want them to be centered around 0, right? Close to 0 as we possibly can. That's good, right? Whether it's negative or positive, it's not really material unless there's a trend. Right? If there's a trend positive or a trend negative, that's kind of bad. Right? And again, it usually indicates that there's the model format that we're using. The specification for that model perhaps is incorrect, needs to be reevaluated. But this is nice. It's all centered around the residual average value of 0. It's randomly patterned, and everything is good. If we were to see any pattern in there, a nonlinear pattern that looks like a big smile or a frown, or a linear pattern that looks like it's going up or it's going down, these all indicates problems with the model. We also see if there's a funnel shaped, where it's more widespread, the higher the x is, and it goes like in a funnel, that's bad. Or a reverse funnel, that's bad too, okay? So let's consider an example here. We're trying to predict salary, and we have a few basic variables. One is job classification. Now, job classification, we have 3 job classifications in this scenario. So we have potentially 3 dummy variables, one of which gets designated as the base case so that we don't fall into the dummy trap and have perfect multicollinearity and nasty stuff like that. So we make professional the base case, and now we compare management 1 or 0, admin 1 or 0 to the professional job classification. We have the age of the employee, and we have a gender variable, 1 female, 1 if female, 0 otherwise, and then years of service, number of years employed. So we have a mix of quantitative variables like age and years of service, along with some dummy variables like job classification and gender. So we do our regression, and here we have it in R, just to kind of mix it up a little bit, just so we don't get too comfortable with Excel, because Excel may not be the stats package that's used in every single case. R is open source, so the price is right on that one, i.e. it's free. So it wouldn't be a big surprise to see this in the workplace as well, R. So we have salary, we have our regression equation, and we look at the estimates, and we see, okay, the estimate intercept is 75,417. What does that mean? Well, that's sort of, if admin was 0, age is 0, that's a little bit weird, right? So probably not true. And then female, okay, so it's not female, so it's male. And management is not management. So we're looking at a professional person just basically starting out. Age is equal to 0. That kind of makes it a little bit funky. Probably not likely. Okay, so we may not have a good interpretation or practical interpretation for this intercept because the age is 0 is a little wonky. However, we kind of squeeze over there and we see that age is not significantly different than 0 anyway, so it probably doesn't matter. We see that years of service doesn't matter anyway, so it's probably 0. So this intercept could represent, or pretty close to representing, the average salary for the base case of professional. Okay? And we can see that admin makes less on average, the negative number there, about $22,825 less than the typical professional. Management makes a significant amount more on average. So the average management person makes $50,593.55 more than the average professional person. And we can kind of see the variables that are significant. Admin is significant, management is significant. So the job classification is a significant predictor of salary. Doesn't look so much like age, gender, and years of service are. However, to be entirely sure that we should eliminate those 3, you could do a partial F to see if those 3 combined belong in the model or not, right? Because there could be a little bit of multicollinearity between, let's say, age and years of service that's making it difficult for the regression calculation to split out the effective age relative to the effective years of service, okay? So we would be looking at some maybe further analysis here. The multicollinearity issue also we can kind of see because these coefficients aren't what we would expect. As you get older, you make on average less. Typically, no. As you have more years of service, you're making $40 a year less. We're skeptical. We're dubious on this, right? So kind of concerned that there might be a little bit of multicollinearity between age and years of service that we need to further investigate. So before we just threw them in the trash can, we would do a partial F to make sure that there's not a joint effect between the 2 that's in the model, that's good to be in the model, that if we remove it, we'll lose that. Okay. Nevertheless, we see the adjusted R-squared of 0.6495, so 65% of the variation in salary is explained by this model. Pretty good. F-stat, very large, right? And so p-value on that is very, very small. So the model in its totality is significant. Okay, so that's really good stuff. Okay. So our next step is we're going to take this data set and look at it graphically. Look at those errors. Okay, we're going to examine this idea of non-constant variance. Is the variance in salary the same across all the X's? Specifically and most glaringly between admin, management, and professional. So what we have is we have a couple of ways to see if that variance error term is constant. We have the graph, which is good. A good starting point for the graph. Can get really mucky when you have many X's, though. There is a test, and it's called a Breusch-Pagan test. It's named after two statisticians who derived this test, and it is a test for non-constant variance. The problem with non-constant variance is our statistical tests are what we consider inconsistent and unreliable. If we're not sure what the errors are, and for almost all our statistical tests, especially for the in the t-tests and in the f-tests, in the denominator is some measure of variability of error, right? Whether it's the standard error of a coefficient in the terms of a t-test, or whether it's the variability in error in the case of an f-test. Okay, so in both of those kinds of tests, error is in the denominator, and if we're not sure what that error is in any specific case, we're unsure about tests for significance for coefficients or tests for significance for the overall model. Okay, so it really makes a mess of things. However, with those graphs, we can plot the values of those residuals, and we have studentized and t residuals. Those are just fun. We'll just call it, maybe they're very similar. They just are slightly adjusted. Okay, but the style of adjustment's not super important in our context. Okay, or we could look at the y hat, not the y's, but the y hat against the residuals. Not okay, and so those are two ways that we can look and see if there's a pattern there. Now we're going to use some fancy terminology. If the variance of the error term is constant, we assume it to be homoscedastic. Okay, all the same. If the variance changes as x or increases or decreases, we say that the variance is heteroscedastic. Whoa, right? Fancy words, makes you sound more important. Now, Excel is sort of a package that was designed for very simple number crunching, mostly for accountants. And then later on, it's sort of thought that, hey, we should glue on some stats here because a lot of folks are using this for statistical procedures and just try to make it a little simpler that way. So Excel has some simple stats functionality, but not involved stats functionality. So for instance, we couldn't find VIF in the multicollinearity case easily without doing a lot of our own little macro in Excel. The same story for this heteroscedasticity. We don't really have good testing for that. So we then depend on other statistical packages to deliver that for us. Excel is very nice at displaying the data, finding graphs on the data, and doing that initial number crunching. Very, very useful, very, very easy, and very, very user-friendly. Once you start to kick it up a notch and get into a little bit more involved statistics, it starts, the wheels on that bus start to fall out. Wait till you try to do Excel regression with very, very large sample sizes, and you could really see it chug. It's kind of funny. Okay. So we have this Breusch-Pagan test, which we will conduct. I will conduct it using R and present the results to you. So if you're sitting there, how the heck do I do this on an exam? I will do the Breusch-Pagan test and then present the results to you. And so it's beyond the scope of the class to do this calculation, but it's good to know that it's there. It's good to know that there is a test for non-constant variance. Okay. So what's nice though, what's nice and what's very convenient about the Boyce-Pagan is very, very available. And if you use R, if you use SPSS, if you use any of those other statistical package, this is like a standard go-to test for heteroscedasticity. So it's really easy to work with in that regard. Okay, so it's very, very prevalent, doesn't require any special tweaking in a stats package to get this result. Okay. So it's a chi-square test, which is awesome because we've done chi-square test stuff now, so we know how that's distributed. The degrees of freedom is p minus 1. P being what p was before, the number of x variables, the number of independent variables minus 1. Okay. Now, if the errors are constant, we don't expect a relationship between those independent variables and the residuals. Okay. So what that really means is that when we start to look at our HO and our HA, our HO is that the variance is constant, i.e. homoscedastic, unless we can show that the variance is not constant, i.e. we have to show that it's heteroscedastic. Okay, so we assume, because it's an assumption, right, we assume the errors are normal, right? It's an assumption of the linear regression calculation. So to show that it's violated, we have to show that that assumption is invalid. So we assume it's good, everything is good, nothing to see here, unless this test shows us otherwise. Okay. Other than that, it's a Boyce-Pagan, it's a chi-squared distributed variable, right? You know, chi-squared, you know, CHI dot and then dot dist, and depending, it's just straight right-tailed. So there's no right tail, left tail kind of issues. It's all right tail. And you're done. You're done. Easy peasy, right? You can use Excel to calculate the p-value when you get this, when I provide you with this Boyce-Pagan test statistic. You can use Excel to come up with the p-value nicely and easily. And then you take that p-value, you use it in the normal course of life here, right? It's the normal, regular 6-step process, right? And nothing is different, right? The only thing that changes is what are we testing. So in this case, we're testing that the variance is constant versus the variance is not constant. Okay? So words, no Greek letters here. Alpha, step 2, it's the same old alpha, right? Test statistic, well, that's that Boyce-Pagan test statistic and its degrees of freedom. The Boyce-Pagan test statistic is a chi-squared distributed variable, so we would expect it to be, to have a degrees of freedom like every other chi-squared distributed variable. We find the p-value using Excel. If you want to kick it old school, you can use the tables as well. But we can use Excel for that. And usual functions that we've used before to find the p-value. Right? Really, no different. No different. Other than everything is right-tailed here. Okay, so there's no right tail, left tail. It's all right-tailed. And then we make the decision by comparing that p-value to alpha the same way we always make that decision, comparing the p-value to alpha. Okay. And then inclusion. We really only have 2 choices here. The variance is constant or the variance is not constant. Okay, it's one or the other. Right. So it's a very simple conclusion here. It's this or it's that. Boom. End of story. Okay. Let's look at the test structure in the context of this regression problem that we're working on. Okay, so we'll test to see if variance is constant or not. So we start with our step 1. And our step 1, we have an HA and HO and an HA. And HO is that we assume that the variance is constant. Okay, because this is an assumption we make. And unless we can show that the variance is not constant. Okay, so HO is the variance is constant. HA is that the variance is not constant. Step 2 is alpha. Just like step 2 is always alpha. And we could pick, and I'll just pick a random alpha of 0.06, without really getting too far into the weeds on type 1, type 2 error here. Step 3, this is a Breusch-Pagan test statistic here. It has the degrees of freedom. Okay, and the Breusch-Pagan, that'll be something practically that you would use R to define, or SPSS. Probably R would be the most prevalent, and we'd find it. As far as we're concerned, I'd be provided it to you. So if I provided it to you, it would be a really, really big number, in this case of 368.32 with the degrees of freedom of 4. Okay. Don't forget the degrees of freedom of 4. It is a chi-square distributed variable, and like every single chi-square distributed variable we deal with, it has a degrees of freedom as one of its important parameter. Step 4 is the p-value, and the p-value is the p-value, which means it involves Excel for us. So Excel moment here. Okay, so we use Excel, and it's a chi-square distribution. So chi, just like we have, square dot this to get a p-value. Now you see this RT and not RT. This is all right tail test. So that's not 100% intuitive, but it's a right tail test. So dot RT bracket, and then I punch in my numbers, 368.32, comma, degrees of freedom of 4, close that bracket, and I get a really, really, really small p-value. It's a little bit modern version of Excel, carries it to a lot more zeros, so it's 1.94 times 10 to the minus 78. Okay, so it's lower than the lowest number that this version of R could handle. So anyway, p-value is really, really small, 1.94 times 10 to the minus 78. No matter what, this p-value is definitely less than or equal to alpha. Therefore, we do reject H naught with that particular value of alpha, pretty much with any value of any reasonable alpha. And step 6 is the variance is not constant. Okay, so we have a problem here. Houston, we have a problem. And variance is not constant. Okay, so we'll talk a bit about what to do next. Mostly the fixes are beyond the scope of the class, but it's good to be aware of what those potential fixes could be. So bye-bye, Excel. Okay, so now what? Okay, we'll get into that in a second. We also could look at the graphs and we go, okay, looks like a problem here. Look at those managerial folks, pretty wide distribution. Actually, for the professionals and for the admin, it's fairly constant. It's actually not too bad between those two. However, managerial salaries, they're just all over the place, from really, really low, junior trainee kind of thing, to really, really high CEO and vice presidents and all that kind of good stuff. Okay, so quite a wide range. There's the p-value in case you're not sure. And so what happens? So the model was significant. Okay, regression models satisfy the error mean had 0. That's usually restricted by the nature of how the least squares regression calculations are done. The error does not have a constant variance. This is for sure. Errors are independent of each other. Not going to be too big an issue unless we have, because there's not a time series. However, we'll deal with autocorrelation coming up. Errors are normally distributed. We could do a graph to verify that. So because the errors are not constant, it could mean that there is some problem here. And some of the problems are we're trying to fit a linear relationship where the relationship is actually nonlinear. Hard to say here. Also, perhaps missing variables. Maybe we need to segment out that managerial class a little bit better. Okay. Clearly, there's a lot of heterogeneity in there, i.e. a lot of variability. And when you think about that managerial grouping, again, you could be from the trainee up to vice presidents and and presidents and CEOs and stuff like that. And that's a pretty wide-ranging group. So we may want to consider splitting that group up a little bit to, lower management, middle management, upper management, just kind of thing. We don't know. We can't tell immediately. It's we try something and we see if it works, and if it fixes it, awesome. And if it doesn't, we come up with something else. Okay, so it's a journey when we do this. Okay. So again, errors will be zero, like I just said. For autocorrelation, because this is not time series data, it's not going to be too big an issue here. However, if it were time series data and we had errors that were related to each other, we'd use the Durbin-Watson test statistic to find for autocorrelation, which is coming up into one of our future units. So very, very exciting. Anyway, that concludes this part. Now we're going to go and talk a little bit about outliers and leverage next. Looking forward to it.